Hello, students, and a very warm welcome to today's explainer. This lesson, created by Mindsticks Foundation Trust, dives right into a force that is completely invisible, yet literally keeps us grounded. We are talking, of course, about gravitation. Let's get right into it, shall we?
Here is what we'll be looking at today. Number 1, the phenomenon of gravitation. 2, circular motion and centripetal force. 3, Kepler's laws of motion. And finally, 4, the universal law of gravitation. Okay, starting with Section 1, the phenomenon of gravitation. So, what do you already know about gravitational force? You've dropped things, you know they fall. You know it stops us from just floating off into space. Take a quick second to think about your own everyday interactions with gravity. Now, we've all heard the famous story of Sir Isaac Newton and the apple, right? He saw it fall, and it sparked a really brilliant question. He didn't just casually watch it hit the ground. He asked himself, why does the apple fall strictly vertically downward? Why not at a slant? Or, for that matter, why doesn't it just fly off sideways? Well, after some serious thought, Newton realized that the Earth itself must be actively pulling the apple. And more importantly, this attractive force is directed exactly towards the center of the Earth. So, the direct path from the apple up on the tree down to the Earth's center gives us that perfect vertical drop. This is where Newton's genius really shines. He took that simple, everyday observation and scaled it right up. He figured, if gravity pulls an apple from a tree, could it be pulling things much, much farther away? Like, say, the moon, or even the other planets? Keep that massive question in the back of your mind.
To answer that, we move to Section 2, circular motion and centripetal force.
Let's try a quick mental experiment. Imagine whirling a stone tied to a string around in a circle. Are you applying force? Absolutely. You're constantly pulling that stone towards your hand, right towards the center of the circle. If you were to suddenly let go of that string, the stone wouldn't keep going in a circle. It would just fly right off in a straight line, tangent to the circle. There's a specific scientific term for this exact pull. Whenever a force acts on an object moving in a circle, directing it towards the center, we call it centripetal force. The word literally means center-seeking. It's this continuous center-seeking tug that stops the stone from just flying away.
Now, let's connect the dots. Just like your hand pulls the string to keep the stone circling, the Earth exerts an invisible pull on the moon. For the moon to stay in its orbit, something has to be pulling it inward constantly. That something is the Earth's gravity. Gravity is the centripetal force for the moon.
Okay, let's shift gears a bit and look up at the stars. Section 3, Kepler's laws of motion. Long before telescopes, astronomers like Tycho Brahe spent years meticulously tracking the planets with just the naked eye. Johannes Kepler then took all that brilliant data and made a huge realization about planetary orbits. They aren't perfect circles. They're actually ellipses. Think of an ellipse as an elongated oval with 2 focal points. And the Sun? It sits at just one of these focal points, not dead center. From this geometry, Kepler formulated 3 empirical laws. First law, the orbit is an ellipse with the Sun at one of the foci. Second law, the line joining the planet and the Sun sweeps equal areas in equal intervals of time. And the third law, the square of its period of revolution is directly proportional to the cube of its mean distance from the Sun. But here is the kicker, students. Kepler figured out the how perfectly, but he actually had no idea why the planets followed these rules.
Which brings us to our final piece of the puzzle, Section 4, the universal law of gravitation.
This is where Newton steps in and brings it all together beautifully. He took Kepler's observational laws and combined them with his own theories on forces. Imagine any 2 objects anywhere in the universe, let's call their masses m1 and m2, separated by a distance d. Newton proposed that absolutely every single object in the universe attracts every other object with a definite force.
And we can actually write this out mathematically. F equals g multiplied by m1 times m2, all divided by d squared. Basically, the force gets stronger if the objects are heavier, which is the proportional to the product of their masses part, but it gets weaker the farther apart they are, which is the inversely proportional to the square of the distance part.
Now, you might be wondering about that capital G in the equation. That is the universal gravitational constant. A brilliant scientist named Henry Cavendish actually measured this later on through experiments, and it is a tiny, tiny value. In standard SI units, it is 6.673 times 10 to the power of minus 11 Newton meters squared per kilogram squared.
I want to pause on that inverse square bit for a second,
because it's super important in reality. If you double the distance between two objects, the gravitational pull doesn't just cut in half. It actually decreases by a factor of 4, because 2 squared is 4. So you can see how this force drops off incredibly fast over large distances.
This whole synthesis was just a massive scientific achievement. Newton didn't just guess that equation. By using his theory of gravity, he was able to mathematically prove Kepler's laws. He perfectly connected the everyday physics of a falling apple directly to the exact cosmic mechanics governing our solar system.
So, as we wrap up this explainer, I want to leave you with something to really think about. If Newton's law is correct and every single object in the universe attracts every other object, that means you are currently attracting the desk right in front of you. You're even attracting your classmates sitting at the next desk. So, why aren't you and your classmates physically sliding across the floor towards each other right now? Think about the massive size of the Earth compared to you, that incredibly tiny value of g we just looked at, and the friction on the ground. I'll let you ponder that one. Thank you for tuning in, and keep learning.